Alright, cool. We are up and running. How is everyone today?
Doing good.
Doing better than my audio system. Alright, well, welcome back from a really, really long break from this class. So, yeah, it's Wednesday, but it's Monday. So let's see. I graded PA1. PA1 grades are posted. There's a lot of feedback on them if there were any deductions or if there were issues that maybe didn't cost you points but might cost you points in the future. So make sure you look over the comments even if you're completely happy with your grade, even if you got 100%. And yeah, that's an act I'm working on where I teach and I look like I'm not moving. It's a little trick I do sometimes. Exactly. So, but I have an app for that, Wallcam. Let's see what this does. Ta-da! No hands. And bingo. There's our countdown. All right, so PA1 is graded and grades and comments are posted. And by and large, it looked good. People mostly got their linked list codes to work, which is awesome because you're going to use your linked list code again for PA2, so that's good. And lots of good grades. Lots of slip day usage. More than half the class took at least one slip day. So those are being used. Remember, you have a total of 4 for the entire quarter, not 4 per assignment because that wouldn't make any sense. All right, so I'll go really quickly through some comments on PA1, but I talked extensively about PA1 in yesterday's class, so you're welcome to watch the video from yesterday's 222 class. We basically lose a week of class in this section because we have 2 Monday holidays and we only meet 2 days a week. So that's basically a week of lecture that we're going to lose in this section compared to the other. So in the B section, I've gone through, some things that are sort of a little peripheral to the core material of the course. And so if you're interested, you can catch those in Tuesday's lecture. Or Thursday's lecture from last week. But let me talk about PA1 in a little bit of detail in here, and then we'll finish talking about Qs, and then we'll talk about PA2, which is posted. So let me hop into my. So, the main grading rubric, I mean, this was from the assignment with a few changes. Obviously, if there's no submission, you lose full points on it. If your tar file was not readable, that's a problem. And I think some people are using Windows and they're building their tar file on the Linux machine, which is great. And they look at it on the Linux machine and it looks great, but when you transfer it to your laptop, if you use something like WinSCP, you might have to set it to say do a binary transfer instead of an ASCII transfer, to make sure that, because a tar file is binary, it's got non-human readable stuff inside, and if you were to transfer it as, say, a plain text file, it will be corrupted. If you're unsure whether that's happening or not, the thing to do is after you've got your file on your laptop, push it back to the Linux machine, right? And then on the Linux machine, go copy it into an empty directory, untar it, say make, run your test code, and make sure that everything still works. Yeah, I thought it was set to binary by default also, but I think at least one case it ended up transferring as an ASCII file. So you can always do that to double check, right? Or better yet, put a Linux system on your laptop, either in VirtualBox or something, so that you can copy with just SFTP, and then you're all set for later in life. Missing files. If your program does not compile right for PA1, I was willing to try to fix your compiler so I could test your code, but it costs you half your points if I have to do that. But it's better than losing 100 points, right? So so I did that for PA1. I'll probably do that for PA2. I may not do that going forward though after that. Good make files. So everybody had a make file, and the make files built the target the way they were supposed to. One small detail: make sure you have a clean target, and make sure the clean target does not just remove star.o. Make sure it removes exactly the files you want to remove and nothing else, because star.o could mean 1,000 object files that the person has in this directory, and you don't want to remove those if they're just trying to clean up the files that you created. So your make clean should never remove star.o or main star or something like that. It should name exactly the files you want to remove for this class, right? For other scenarios, wildcards might make sense. But in the instructions, when it says, make sure you remove exactly the files you want, that's what I mean. I am being really, really specific about the style aspects, the program style, the organization of it. According to the assignment. So your node has to be called a struct mynode. It has to contain an integer data and a struct mynode star called next node. Data has to come first. The order of these is critical. If you switch these around, the poor CPU has no way of knowing that you wanted the data to come first. It just sees bits in memory. And if you declare your node sometimes like this and sometimes with data second, everything's going to get jumbled up. And you'll know that because your code simply won't work. And then you needed 6 functions with exactly these names, exactly these prototypes, exactly these types of return values, and exactly this behavior. And then you needed your program split up into 4 files. So main, functions, main.h, and a make file. And I was being very, very dogmatic about that requirement. And so lots of point loss if you vary from that. The reason I'm being so dogmatic is not because I can't figure out, that you named your functions, function instead of functions or something like that. The reason I'm being dogmatic is because, in university classes typically, your submissions are graded by, some overworked grad student who's got 200 things to grade before they can do their work, and they're going to write scripts, and they're just going to feed your submissions into these scripts. And if you've got the wrong function name, or it's called a struct node instead of a my node, their script's going to say I can't compile it, and you're going to get a 0, and that's it. And after school, when you're on the job, you're working in part of a project, you're going to take what you're developing and hand it off to someone else, and they're going to integrate it into other parts of the system. And if you called your function, a init with an uppercase I instead of a lowercase I, everybody who's trying to use your code, they're going to get compile errors. And people are going to yell at you, and your boss is going to talk to you and say, hey, why aren't you doing what you're supposed to be doing? It is really, really that important, right? And this is a sort of low-cost way to get practice with that. So so definitely be absolutely sure you're following the assignment specification to the letter, right? And if you have any doubts about what it means, or is this important or is that important, just ask, right? But ask ahead of time. Don't ask me 7:30, Friday morning. So that's the business with, does not match the required names, prototypes, not split into the proper files, and so on. The functions themselves, good job with those. So a few issues with delete, a few issues with add. And a lot of times when I saw people having issues with these things, it looked like they were doing something different from what we've done in class. and it's like they decided to just try to figure out on their own how to implement a linked list, how to move down a list, how to skip over the sentinel, how to deal with inserting at the end of the list. And that's great. I've got no problem with people, you know, figuring this stuff out on their own. But if you're having trouble with it, if your code's not working, come back to your notes, right? And look at what we've done in class. We've done pseudocode for a lot of these things. That gives you kind of an outline of the steps. And if you find that you're, you know, doing 3 extra ifs in the beginning before your loop, or your loop is, you know, exiting on some other condition or something, go back and think about what we've done. Review your notes, ask questions, right? And I'm trying to give you at least a way to do the things that you're being asked to do. There's lots of other ways to do them. And I'm not saying you've got to do it, you know, exactly the way that I said. But if you're doing it a different way and it's not working, come back and look at the way we're doing it in class, and then maybe modulate from there. Main program, you know, was only worth 10% of your grade. So I told some people who were having trouble with main, like, don't worry about it, you know, eat the 10 points. And just write a main program that does something, that compiles and runs, so that I can, you know, verify your make file is good and there's no compile errors and so on. And then, you know, I'll use my own main program to test your functions and so on. So some people did that. But, you know, the main program is basically a rehash of 224 assignments, where you're reading an input and parsing it and then calling functions in response. Not a lot of memory leaks, which was fantastic. People are freeing their memory, which is a really hard thing to do. And you know, at third year, fourth year courses, teachers are still kind of yelling at their students, like, if you have any memory leaks, you're going to get a 0, because most people write code with leaks. So if you're managing that right now, and you know, you're writing code that Valgrind is happy with, you're way ahead of the game. Right, so that's going to help you well. So keep doing that. Keep thinking about the memory leaks and so on. And not a lot of warnings from Valgrind either, which was great. So everybody was initializing, you know, things to null if they wanted it to be null, and so on and so forth. Not too many compile warnings. Commenting. So most people lost points from these areas. Either not putting in comments throughout the code, right, and anything that's not, you know, absolutely crystal clear is something that you should have comments on. Commenting in your main program, right, is important. Having a block of comments in the beginning of main with your name, the date, the class, a description of the assignment in your own words, that's all essential. And then having a block of comments before each function, you know, before the code of each function, that basically says, what's the function do? What are the inputs? What are the outputs? What are the assumptions? What are the side effects? Things like that. And then a consistent indenting style. So someone commented on memory leaks in chat. Valgrind will not necessarily tell you where the memory leaks are coming from, but it will tell you that there are memory leaks. What Valgrind is really good for, though, is if you compile with a G switch, like you're going to debug, and you have things like, you know, blocks of memory that you're not initializing when you should be, it will tell you very specifically where you've got issues with that. It'll say, you know, uninitialized value at main.c line 37, and you can go right there and see what you're doing. If you're getting leaks, right, it won't necessarily tell you where, but you can start simplifying test cases, right? Run your program and just exit without doing anything. See if you get a leak. If you do, well, it's not in the add, it's not in the search, it's not in the delete, it's in your init, right, or something else you're doing. Add one node and then delete it, and then exit. If you've got a leak, your delete function is not freeing memory, or you're allocating extra memory somewhere. And then, you know, run your program, add a node, exit. If it's giving memory leaks, your cleanup function's not working. So you can sort of narrow it down like that to some degree. So let me just briefly run through an example solution. So this was my version of PA1. So there's my include file that I forgot to put comments in because I wrote this late at night. But you know, declaration of a structure and function prototypes. Make file, which you know, pretty much everybody's make file looked like this. And I put a -f on my remove to say, you know, even if this file doesn't exist, keep going. Don't give me an error message. But this will forcibly remove these files. If I happen to write protect one of these files, this will still remove it. So that's a little bit of a heavy-handed flag to use, but it avoids some errors. So if I say make clean twice, it doesn't complain.
I would like to say that I was confused about what the clean was supposed to be implemented in. That's why I didn't include it.
So clean is there. So you know, if you make your file, you've got your executable program. And if you say make again, it won't recompile anything. So to force it to recompile, you have to remove those .o files, and you have to remove the executable. And so, you know, you could go in and you could say, you know, remove functions.o, main.o, and main. But make clean will do that for you. And most make files will include a clean option that will get rid of the things that the make file builds. And the typical way to use that is, you know, you've got your code and it's running great here, and let's say I want to take the same program and run it on a Raspberry Pi, right? If I just copy all of these files over to the Raspberry Pi, my main program will not run because it's a different CPU. It's got different, you know, machine code and so on. I need to recompile it, right? But if I just say make, it's going to say main is up to date. And so the only way I can get this to recompile, you know, in a different environment is to first remove the things that were already compiled. And if you've got, you know, 12 directories with, you know, 5,000 different object modules scattered around, you don't want to have to try to delete those yourself. So the person who creates the make file puts in a clean option, and then you just know you can say make clean and then make, and it'll recompile. So that's the basic setup for that. All right, so main program, you know, there's the class, there's my name, there's the date, and here's a description of what this program is. It's a linked list package plus a main program for building, examining, manipulating, and freeing a linked list. And then, you know, brief synopsis of what the user can do here. You can basically interact through a series of simple commands. Here's a, you know, sub one line description of each command. And for insert, delete, and search, the user also specifies an integer following the one character command. Values are added to the list, so the list is always sorted from smaller to larger. So that's, you know, that's not the whole write-up of PA1, but it gives you an idea, you know, is this a game I can play? Is this something that will browse the web? You know, oh, this is a linked list package plus a program for interacting with it, right? So it's just sort of the executive summary of what's going on, plus, you know, your name and such. And so I have some function prototypes, and then my main program. And, you know, my main program, there's the pointer to my Sentinel node. There's a temporary buffer I use for reading user input. I call the init function to create my empty list. I print out a prompt, and then here's my whole main loop, right? I call fgets to read a line of input from the user. I call this process function that will do whatever the user asked the program to do, and then prints out a prompt and goes back. So it's basically, you know, read, process, output. But then the process command, if the person says, you know, X to exit, it will return a 0. And so if it returns a 0, I break out of the loop, I call my cleanup, and I'm done. So that keeps my main loop, you know, small, so that, you know, if I'm testing this, if I want to do other things in here, if I want to print out, you know, debug statements and so on, I'm not dealing with all of the scanf and parsing and all that kind of stuff. That's all buried inside this function called process. And so process, you know, basically takes a command and a pointer to a Sentinel node, and it examines the command and if there's an error, it'll print an error. If there's not an error, it'll do what the command says, and then it'll return either a 1 normally or a 0 if we got the exit command. And so this is, you know, the CSE222 stuff where we do the scanf, we pick up extra stuff with a %s. And, you know, I switch on the first character. If their command starts with an I make sure it's I followed by an int. And if it is, you want to add something to the list, I check to see if it's already in the list. If it is, I print an error message. Otherwise, I go ahead and add it, and I say success. And I don't bother, you know, with checking for memory in here. Otherwise, I print a usage message. So my help message that shows, you know, the legal commands, those are down in the usage function. If the command starts with P, I just go ahead and I print the list. So if they say, you know, pretty, it'll still print the list as long as it starts with a P. If it's an S followed by exactly an int, I'll call search and I'll print out either found or not found. So I'm using a ternary operator here, but you could do this with an if-else if you want. Otherwise, you know, if it starts with an S, but it's not an S followed by an int, I'll print out a help message. And then delete looks exactly the same, except before I call delete, I call search. And if the node they're deleting is not found, I'll say not found. Otherwise, I call delete. And then, you know, I know it's going to succeed because it can't run out of memory, and the node is in the list because search said so. And then X is the exit command, and I just return 0, which will tell the main program to exit. And then anything else I call the help function usage and remind them what the legal commands are. And yes, switches can be nice if you have, you know, a series of things that you you know, if this then do that, if this then do that, and so on. Sometimes that's cleaner looking than a bunch of if-else statements, and it may be faster depending on the CPU, but that's not really a concern. But yeah, so I've grown to like switch statements more over the past few years, but you know, personal style choices. And then functions, you know, is all the stuff that manages the linked list itself. So here's the init function, and you know, most of the functions look like, you know, what most people turned in. But block of comments in the beginning, right? Here's a synopsis of you know, the function prototype. And then takes no arguments, returns the address of the Sentinel node for a new empty linked list. And then I talk about the Sentinel node. The data field has this, and it's set to that value as a flag to help us notice if we accidentally process the Sentinel. And then a little note here, if the malloc fails inside here, the function returns null. Right? If malloc is null, then return value will be null, and this is going to segfault. And so, you know, that's a little disclaimer in there. The add function, right? So there's the prototype and a one-line synopsis. It inserts a node into the linked list. But that's not sufficient, right? And I said in the write-up, you know, saying this adds a node is not sufficient. So what are the arguments? First argument is a pointer to the list Sentinel node. Second argument is the integer to add to the list. Those are useful things to know, right? You know that because you wrote the function. And I know that because I specified what the function should do, but how would you know that, you know, if you hadn't written this yourself, if you didn't have PA1 in front of you? How will you know this 2 years from now when you're trying to dig up your linked list code for something else? The integer will be added so the list remains sorted. That's important to know. And what is sorted? Smallest node next to the Sentinel, largest at the other end. And then a little note here, this will insert duplicates. If you don't want duplicates, you should call search before calling add. And then what does it return? It returns an int. What's that int mean? 1 for success, 0 for failure, and failure means it's out of memory. So if I'm trying to use the add function, I don't have to go through all of this gibberish, you know. I have a you know, more human readable synopsis right here. And that's sort of the goal of having this documentation before each function, is to give you a way to understand the highest level behavior of the function without having to, you know, kind of reverse engineer what all this code does. And even with, you know, comments on almost every line, if you're not familiar with linked lists, it would take a lot of effort to look at this code and figure out, oh, these nodes are being inserted in increasing order. You know, oh, this will allow duplicates. This returns 1 unless it runs out of memory, right? So just putting synopses on the top. Print, you know, basic list traversal and print, takes a single argument, which is a pointer to the sentinel mode, prints the integer value, prints it with a %d format. That might be useful to know. Single line with a single space in between each number and a new line at the end. By the way, there's a trailing space at the end of the last number on the output line, which might be important to someone, right? And I didn't want to bother trying to detect that I'm at the end of the list, and so I'll print a %d without a space, right? So I just have an extra trailing space there. But, you know, might be good to mention that. And then delete, you know, same thing. And by the way, delete does not rely on the list being sorted, which might be interesting to the person. Same thing with search. Search does not rely on the list being sorted. If we did rely on that, if we stopped searching once we got to a number that was on the wrong side of what we're looking for, right, we would get some speed up. It would roughly double the speed, but it would still be order n, right? It doesn't actually improve the order of complexity. So I mentioned that in here. And then cleanup, you know, is the routine for freeing all the memory that we've used. And useful note in here, right? After you call this function, the sentinel has also been released. And if you try to use the sentinel pointer after you've called cleanup, you're probably going to segfault or, you know, hit corrupted data. So I wanted to mention to the user in here, you know, once you call cleanup, any further attempts to use the sentinel will result in unpredictable behavior. So that's you know, just an example, and I don't care how you stylize things, but play around with it. You know, have fun. Let yourself be creative. It's very much a personal choice how you want your code to look. How do you want to, you know, mark off blocks of comments? And that's you know, totally up to you. You know, this is stuff I've been writing the past few days, and it's got like ASCII art inside, you know, and stuff that I really want to stand out. I'm kind of tagging with that, and I'm trying to line up comments next to variable names and so on. But you know, it's personal choice. You can choose your own brush strokes when you're writing code, and I encourage you to do that, right? Because if you know, always initialize variables the same, you always indent a certain amount, you type int space variable name, maybe you put spaces around your equal sign, maybe you put spaces before but not after your equal sign, maybe you put a space before your semicolon, right? But if you always do it the same way, it's going to help you when you're working on your code and you're trying to find issues with your code, you're trying to debug. If you've you know, got wiring in your brain that can just sort of see a pattern of space and non-space and recognize that as a loop, a conditional, an else statement, an initialization, right? That's all going to help you be more efficient. And it's your style, right? It's not dependent on how the knob settings are, you know, tuned in your IDE, or you know, somebody updated the editor and now it's doing different highlighting or different indenting. It's your own style, right? So pick it as your own. Yeah, you can put a space before a semicolon. You can put a semicolon on the next line if you want it to be really awkward. Spaces are mostly ignored except where they're necessary to prevent ambiguity in C. All right, so any kind of wrap-up questions on PA1?
I feel like maybe my delete function is like wasting memory or something, and I don't know how. Like if I'm like changing the address of the next node to another node,
Mm-hmm.
how do I free from memory the address of that the next node was pointing to before?
So let me. This may not be what you're referring to exactly, but let me make a comment on something that I think is related, and then if this doesn't address it, we can go in a different direction. But this is something that I've seen in some code. So for example, struct node temp, and let's say this is add struct node list and so on. So let's say we're in a function definition and we're getting a pointer to a struct node, and I'm going to declare a local variable called temp, which is also a pointer to a struct node, and I'm going to say something like temp equals list arrow next, for example, right? Different my struct, but for an example, if I'm going to do this, I do not want to say equals malloc and so on. This will definitely cost memory, and it will cost memory that you're probably going to lose and not be able to free later. I'm saying here that temp is a pointer to a struct node. When I do this, I'm saying, oh, and pull a block of memory out of the heap and set temp to point to it. Well, there's nothing wrong with that in itself, except a little while later what I do is I say, oh, I want temp to point to whatever list is pointing to. And this chunk of memory that I allocated up here is now lost. And this is completely unnecessary. Right? So doing this would be analogous to saying something like, integer I equals 5, and then saying I equals 0. Right? Why would I give I a value when I declare it if I'm going to give it a different value in the next statement? Right? So we just say integer I, and then we can say I equals such and such. So that's one thing that I've seen is if we're having a temporary pointer like this, right? This is just saying temp is a pointer. Temp holds an address. It's an 8-byte thing. We don't need to free temp by itself. If this is our add function and we're using temp to move down the list, when we're done using temp, we do not need to free it. In fact, we don't want to free it. The only time you need to free something is when you've malloced something and you're saying, let's unmalloc it. Let's put that block of memory back into the heap so that other processes can use it. And so I can do this. Go ahead.
So, what if you free something that hasn't been malloc? Does that waste memory somehow? Or?
If you free something that hasn't been mallocked, it's probably going to blow up. Valgrind will definitely have a fit, but you may seg fault in the process.
Oh.
Because it's going to go through the list of things that have been mallocked and try to find which one corresponds to the thing that you passed to it, and if it doesn't find it, it's going to go haywire. So I would not free temp, for example, if I just said struct node star temp, and then use temp for some stuff, maybe temp equals temp arrow next, and do that in a loop or whatever, right? When I'm done, I can just return, and this is a local variable. The storage used for that is reclaimed. It's only if you allocate memory that you need to free memory. Does that make sense?
Makes sense.
Okay, cool.
It makes sense that the memory for local variables are returned
Mm-hmm.
to RIM after after the function returns. I didn't know that.
Okay. Yeah, this is really no different from that. Right? It does take memory, but it's not coming out of the heap. It's coming out off of the stack actually. And so when you return, that memory is automatically reclaimed. All right. Well, let's continue talking about queues. So, is there a pile instead of a heap? There should be. I don't think there is. So, I believe we already went through the abstract data type view of a queue, which was basically some sort of pipeline, and there's a head at one end and a tail at the other end. And the idea was things enter the queue at the tail and things leave from the head. And it's a FIFO, first in, first out. So if you add an A to the queue, the A will go in and sit up here at the head. If you add a B, it'll go behind the A. If you add a C, it'll go behind the B. And you can keep adding things, but the first time you remove something, it's going to be whatever the first thing was that was put into the queue. In this case, it's going to be the A. So when you remove, A will come out, and now B will be at the head. And if you remove again, B will come out, and C is at the head, and you can add a bunch of other things. And none of that changes what's going to come out of the queue next, which is whatever's currently at the head. So it's a different behavior from a stack. A stack, you put things in here, you take them out from the same end. A queue, you put them in here, you take them out from the other end. So, a checkout queue at the grocery store is one model for this, where things are hopefully taken in order of how they're inserted. All right, so, and I believe we talked about how to implement this. We were talking about how to implement this with a linked list. So let me finish up that. So imagine a Sentinel node. And we're going to represent our queue with a linked list. And basically one end's going to be the head, one end's going to be the tail. And so to add something to the queue, we're just going to, squeeze it in at the head, at the tail, and to remove, we're just going to delete the node at the head. And the way I'm going to set this up, I'm going to have my head right here next to the Sentinel node. I'm going to have the tail at the far end of the list. And so if I want to add, number n, for example, what I want to do is create a new node with an n, and I want to squeeze it in at the tail. So I need to get to the tail, and I can do that by, starting from the Sentinel, moving down the list until I get to a node that points to null. And then I create a new node with an n. And that last node, instead of pointing to null, I simply have it point to this new node that I created. And that effectively moves my tail to, the last thing that I inserted. So this will be the last thing to come out of the queue. And then to remove, I simply start from the Sentinel node. I look at the node it points to. The data value of that, that's the value I'm going to return, and then I just delete this. So I change the Sentinel to point to the thing that head node points to. I free this from memory, and that basically changes the head to be, what was the second thing in the queue. So these are, subsets of the list operations you already did for PA1. The add always happens at the end, the remove always happens at the beginning. So, simpler versions of the functions you already wrote. There's one embellishment we can make on this, right? The remove operation is always order 1, because we're just removing the first thing in the list. It doesn't matter if there's a million things over here. To remove, we just, take the thing the Sentinel points to, delete that. So move one node past it. But the add operation, where we're adding at the tail, the way I've described it, this is an order n. Because we have to move from the Sentinel all the way out to the tail. And order n is not good. We don't want order n. So is there a way that we could make this more efficient? That we can insert to the end of a linked list without having to move all the way through the list?
Could you not use the beginning of the list? I think we talked about this as like some sort of storer of the length of the list, and you just
Something like that. Knowing the length of the list won't help us directly because we'd still have to move that many steps to get to the tail. But we can effectively do that. We can effectively do that by having something else, right, which I'm going to call a tail pointer. Just a separate, like a second thing to go along with the sentinel, which always points to the last node of the list. So the sentinel points to the first node, the tail pointer points to the last node. And this has no impact on our remove operation, because remove happens up here. But when we want to add something to our list, well, instead of moving down the list all the way to get to the last node, we just look at the current value of tail pointer, and we know that's going to point to the last thing on the list. So our add function becomes something like, new equals malloc. So make yourself a new node, set the data field for it, and so on. And then tail pointer next equals new. So, here's our new node. Tail pointer points to this node, so we set its next field to point to new. And then we change tail pointer to be new, so that this now points to that node we just inserted. Now we're all set for the next time we want to do an insert at the tail. So we still have the sentinel pointing to the head. We're not going to break that because we need to be able to get to the head quickly to remove. But we have a separate pointer that points to the tail. And we can use that to come back to order 1. Because now it doesn't matter if there's a million things in front of this, right? This variable that we keep around, just like the sentinel, always tells us where the last node is. And that's totally legal. This only works if you do head and tail, though. If you switch those around, this trick doesn't work. Because if you're removing from here, you have to back up. And unless you have a doubly linked list, right, you can't back up. But we can easily move forward from the tail to a new node. So the order of those makes a difference. All right, so that's implementation with a linked list, and we'll say more about that in the second half of the class. But let's talk about array-based implementations. So when we did stacks, we saw we could implement a stack with a linked list, or we could implement it with an array. And with an array, the trick was we had a stack pointer that said where is, effectively the top of the stack. Where should we, put our next thing in? And so we're going to do the same thing with a queue. And it's worth noting here that, in a physical queue, if you have, a line and people are entering here and going to the head of the line, and then the person at the head gets serviced and people move up, the things in the queue are physically moving location, right? But that's an expensive operation in a computer to, pick up all the things in this queue and move them over one spot. We don't want to do that. That's an order n. So a linked list avoids that, right? That's the whole idea of a linked list, is we can insert something new in the queue without having to move other things around. We don't have to move things out of the way. And so when we implement a queue with an array, we're going to do the same thing. We're not going to actually move the elements in the array. We're going to change where we consider the head and tail of the array to be. And so let me set up an array. And let's just suppose there's 8 things in the array. And I'm going to have a pointer called tail, or t, which will tell me where the tail of the queue is. And I'm going to have a second pointer called head, which tells me where the head of the queue is. And remember, we remove from the head and we add at the tail. And so let's say we want to add, the letter A. So I'm going to use my tail, which is, an index, to say, hey, the tail of the queue is at index 0. So I'm going to store the thing I'm adding right there. And then I'm going to bump up the tail to point to the next spot where I would add something. And now if I add a B, that's going to get stored at index 1, and I'll bump up the tail. And if I add a C, that's going to get stored at, the index pointed to by the tail, which is 2, so that's going to get stored right here, and I'm going to bump up the tail to 3. So here's what my queue looks like, right? Here's the tail, here's the head, so this is the end that's going to be removed from. First thing to be removed will be an A, and then B, and then C. And so I'm just kind of moving the back of the line, right? So let's put a few more things in our queue. Let's put in a D and an E and move our tail down to here. Okay, there's our queue right now. Let's remove something. So when we remove, we look at the head pointer and we say, oh, the head's right here. Let's go ahead and, return the value A, and let's just bump up the head. So now the head points to here. And so this is like, being in line at the store, but the cashier moves down the line as they deal with customers instead of customers moving forward. So now this is the head of the queue. And if we remove again, it's going to give us the element, that's pointed to by the head. So that's a B, and we're going to change the head to be right here. And if we remove once more, that's going to give us the C, and we're going to change the head to be here. So now our queue only has 2 things in it. There's a D, which is at the head of the queue, and then there's an E, and that's the tail of the queue. Does that make sense so far? Okay. All right, so this works great until, let's add an F. That's going to go right here. Tail will come down here. Let's add a G. That's going to go right here. Tail comes down here. Let's do one more remove. So head is pointing to D, so we're going to return the D. We're going to bump up the head. All right, so here's our array. Head is pointing at element 4, tail is pointing at element 7. If we want to add one more element, let's add an H. Tail says, store that at index 7, so there's the H. Well, if we just do what we've been doing, tail is now going to point to an 8. And if we try to add something while the tail is pointing to 8, we're going to go outside of our array. We're going to segfault or corrupt data or something. So from that point of view, it looks like we can't add anything more to our array. But in fact, we have space in our array. These locations up here are all free. Right? We've removed the A, the B, the C, and the D, so these spots are all available. And so rather than saying, hey, we're out of space, you can't add anything more to the array, we're going to take the tail and we're going to roll it back over to a 0. And now if we want to add a J, we'll put that right here at element 0, and we'll bump up the tail. And we still have space in our array. We've got these 3 spots that are open. But our array looks a little funnier now, right? Here's the head. That's the next thing, that's the next thing, that's the next thing, that's the next thing. Here's the tail. So this is acting like a circular array, or sometimes called a circular buffer. And we've basically got this end connected to that end. And this avoids having to, reset the tail and head to move things back, or simply running out of space once you've used all the spots in your array. As long as you're not using 8 spots in your array, there's still space. And so by wrapping the tail around, we can take advantage of that space. So we can add a K, and our K will go right here, and our tail will come down to index 2. And now if we do some removes, we'll remove the E, point the head here. We'll remove the F, point the head here. We'll remove the H, point the head here. If we say remove again, we'll you know, get that H value out, and then instead of changing H to point to an 8, we'll wrap it around and point back to 0. And the next time we remove, we'll remove a J and move the head to here. And the next time we'll remove the K and point the head to here. And now the Q is empty again. So you can visualize this maybe with a different geometry. That looks like this. So we start off with the head and tail pointing right here. Every time that we insert, we bump up the tail, right? Move it to a higher index. Every time that we remove, we bump up the head, move it to a higher index. And you know, if the tail's pointing here and we add something, we'll just go ahead and we'll bump the tail up to the next spot, which in this case would be 0. So when you remove something, you're really just moving the head, and unless we want to, right, we don't actually do anything with the value that we return. So if our head was pointing right here at the F and we said, you know, remove something, we'll tell the user, okay, we just removed the F. We'll move the head down to point to the G. That F is usually still sitting in the array. Just like with a stack, when you pop, you don't actually remove the thing from the array. You just stop referring to it. And if this is an array, there's absolutely nothing to free, you know, using a free call like free malloc, because it's an array, right? We need that memory to be there. But you effectively open up that space for future use. And once, you know, I've removed this and this and this, those spots are available for adding new things in. As long as I don't try to add more things than I've removed, you know, by a total of 8. So my queue can hold, you know, more things than I've removed, but up to a limit. So this codes really nicely. It's slightly more complex than a stack, but not too much so. So let's suppose my array is called Q, and I want to look at an add function, so I want to add n, right? So remember, you know, I've got a head and a tail, which I'm just calling H and T, but if I was typing it, I would call it, you know, head and tail, or Q head and Q tail or something. But H and T, and I'm going to initialize them both to 0. I could have initialized them both to be 4. I mean, that would work just as well. As long as head and tail are equal to each other, that's, you know, an empty queue. So I'll initialize head and tail to 0, and then to add something, I want to add at the tail. So the syntax would be Q bracket tail equals n, tail equals tail plus 1. If tail is equal to 8, set the tail to 0. Right, so this copies the thing I'm trying to add into my queue at the position given by the tail, and then moves the tail up, and if the tail happened to move from 7 to 8, I'll reset it to a 0. And then remove should basically, you know, R equals Q bracket head, head equals head plus 1, if head equals 8, head equals 0, and then return R. So same thing as adding, except we read from the head instead of writing at the tail, and then we adjust the pointer as usual, and we roll it over at 8 in this case, but you know, this would be whatever the size of the array is. And since this is C, we can do this more succinctly. We could simply do something like Q tail equals N, and then tail equals plus plus tail. And we can use our modulo operator to say, hey, you know, increment our tail and then find the remainder when you divide by 8. So if our tail is less than 8, this will just be whatever our tail is. But if our tail is equal to 8, then when we take modulo 8, look at the remainder divided by 8, we'll get a 0, and that'll roll us back to 0. And then same thing here, we could do H equals increment H modulo H. And then is our Q empty? All we have to know is if our head and tail are equal to each other. So when we start off, head and tail are both 0, that's an empty Q. If we add one thing to the Q, let's put an A in here, change our tail to be right here, and then remove one thing from the Q, so remove the A and change the head to be here. Head and tail are both 1 now, that's an empty Q. If we add 1, 2, 3 things, our tail will be 4. If we remove those 3 things, our head will be 4. Head and tail are equal, that's an empty Q. So the isEmpty function is really just, you know, see if the head and tail are equal to each other. The isFull function is a little trickier. And there's a couple of different ways you can do this. One way to do this is to you know, set a flag. And if after you have inserted something into the queue, your head and tail are equal, your queue is full. And so you need to modify this isEmpty function and make sure your queue is not full. Because if we push an A, B, C, D, E, F, G, H and we've never removed anything, at that point our queue is full even though our head and our tail are both 0 again. But an easier way to do this is don't let your array actually fill up. Declare your queue to be full when you have only one empty space left. And now the only time head and tail will be equal is when the queue is empty. But the queue will be full if adding 1 to tail brings you to the head. So you could do something like if adding 1 to the tail modulo 8, right, roll it over at 8, is equal to the head, then you can say the queue is full. And in this case, we're just saying, hey, you can't actually fill up every single spot in the array. If you're in a situation where adding one more thing would make the head and tail equal, that's where the queue is full. And so that's a slightly simpler approach. All right, so let's take a 5-minute break, and then I want to look at PA2. And PA2 is going to be implementing stacks and queues using linked lists. So I want you to know how to implement these things using arrays, but we're not going to code those. We're going to use linked lists to implement these. So we'll come back in 5 minutes, and we'll talk about that. So let's come back at 11:10. All right, so I'll see you in a few. Say again?
If we made any mistakes on PA1, should we fix them ourselves before we go on to PA2?
So I actually mentioned in the assignment that it's up to you how much you want to reuse the code. You'd need to modify some of it, but if you have PA1 working pretty well, it will be a lot less code you have to write for PA2. So it may be worth, spending some time getting that worked out. But don't spend time worrying about the main program, for example. I'd say at some point before the midterm, you'd like to understand, if you didn't get delete to work or you didn't get add to work, you'd like to figure out the details on that. But for PA2, you can start from scratch, and the add and delete functions you need for PA2 are simpler than they were for PA1. So don't spend a week trying to pin down the last bugs from PA1 and then not have any time for PA2. But sometime definitely figure out those details. All right, I'll be back in a few. Yeah. Yeah, what's up?
Your PA2 document has a blank page between page 5 and the PDF.
Oh, okay.
Also, it mentioned something about I haven't looked at it, but I was hearing earlier before. It mentioned something about a GitLab repository and naming it something like stack queues or something like that.
Oh. Yeah, I wrote this late at night. Let me clean that up.
Good old LibreOffice.
Yeah. Deliverable submission should include a proper make file. Yeah, forget about the Git stuff. All right, let's see. So PA2, some typos in there. So ignore what it says about Git, and I'll post the new version of PA2 after class, because we're not using Git. All right. So programming assignment 2. Let me go off the PDF. All right, so this is a program written in C that's going to let the user interact with stacks and queues. And your program is going to create one stack, one queue, and let the user add and remove and push and pop and display the contents of the stack and queue independent of each other. All right, and there's sample code available on the server that you can look at to see what the program should do. So let's go through the basic details. So you're going to make two things, right? A package, collection of function calls to implement stacks and queues, and then a main program, which is, you know, like the main program in PA1, command line interface that people can use. Since your program is going to implement both a stack and a queue, the user needs to say which of those two data structures they want to interact with. And so this is going to be stateful. There's going to be two modes in which your program can operate: stack mode or queue mode. And the user can switch back and forth by using the command S for stack mode, Q for queue mode. Additionally, the S and Q commands are used to print the current contents of the stack or the queue. All right, so you run your program, you start off in stack mode. And basically, you can add something to the stack by just typing an integer followed by enter. Or you can remove something from the stack by just hitting enter with no integer. All right. If you type something in, you hit enter, it just pushes it on the stack. If you hit enter with nothing else on the line, it will pop the top of the stack, print out what value was popped, and that's it. And then if you type a queue, you'll switch into queue mode. And now if you type a number, it adds it to the tail of the queue. If you hit enter, it removes whatever's at the head of the queue and prints it. And so S goes into stack mode, Q goes into stack mode, and those commands also print out the entire contents of the stack or queue. So even if you're already in stack mode, if you want to see what's in the stack, you just use the S command. If you want to look at the queue, you type a queue to go into queue mode, and it'll show you what's in the queue. And you can add some things, remove things. If you want to see what's in the queue now, type a queue. You're already in queue mode, but queue also shows you the contents of the queue. All right, X is used to exit the program after freeing all memory. Anything else gives you an error message. And again, you know, the usual protocol, right? Don't print any stray output. Don't print any extra error messages. Just you know, do exactly what's described here. When you add something to the queue, don't say, you know, I added an element, right? That's what Windows does. It tells you everything that it does, even though you're the one who told it what to do. You delete a file, it says Windows deleted a file. So don't do that, right? When you push something on the stack, just push it on the stack. All right, implementation. So you're going to implement the stack in the queue using linked lists. And you can use the same linked list code that you did in PA1. You can modify it, right? Because we don't need to add in sorted order. We always need to add, you know, at the beginning or at the end, depending on the structure. And the same thing for removing or popping. But you can reuse that code. We're using the same struct mynode with the int data and the struct mynode star next node. So all of that's the same. The cleanup function can be identical to what you used in PA1. And then the print function, you just need to make some tweaks to, because the print format has to be very specific. All right, so these are the details we've been talking about in class, right? For the stack, push new elements by adding a node immediately after the sentinel and then pop from the same location. For a queue, remove from the head and add to the tail. The head is the node immediately after the sentinel. The tail is at the far end of the list, right? So you add at the far end of the list, you remove from the node after the sentinel. All right, you probably won't run out of memory when you're working with this. The tests I'm going to use are not going to try to run out of memory, and so don't worry about memory issues, right? If the user tries to remove an item from an empty stack, your main program should print an error message. If the user tries to pop an empty stack, the main program should print an error message. But don't corrupt your data structures, right? That's a user error. It doesn't mean you should damage your memory or seg fault or something like that, right? And when you move between stack mode and queue mode, that doesn't change the contents of those data structures. It's just saying, right now I want a view of the stack. Now I want a view of the queue, that kind of thing. So there's your struct my node, right, from PA1. And you're going to implement 11 functions. 5 for a stack, 5 for a queue, and then a cleanup function. So your functions are basically, stack init, which initializes an empty linked list, returns a pointer to the sentinel node. Stack push, which takes a sentinel node pointer and a number, pushes it on the stack. Stack pop, which takes a sentinel node pointer and returns the integer value for whatever's at the top of the stack. Stack is empty, which takes a sentinel pointer and returns 1 if the stack's empty, 0 if it's not empty. And then stack print, which prints the contents of the stack in this very particular format, TOS, -- greater than, followed by a space-separated list of the values in the stack, with the thing at the top of the stack appearing on the left. All right? And a little warning here, it's got to look exactly like this. If you do it in the opposite order and put TOS on the right, you're not going to get points. Right? So exactly like this. And then the same 5 functions for queues, but, queue init, which initializes an empty linked list, right? And these can probably just call your init function from PA1 and return whatever that function returns. Queue add, which, will add in a new node at the end of the list. Queue remove, which removes the first node in the list. Queue is empty, which tells you whether or not the queue is empty, and that's going to look an awful lot like your stack is empty function, which basically just looks to see if the sentinel is pointing to null. And then queue print, which is going to look, a lot like your print function, but I want you to print out head -- greater than, and then space separated list of numbers, and then, less than -- tail. And so this is, just your print function from PA1. This is just your print function from PA1, but throw these tags in the beginning and the end to indicate where the head and tail are. And then cleanup is the same cleanup from PA1. Just march down the list, release all of it. So it just takes a pointer to a sentinel node for the stack or the queue. So it's 11 functions, but it's very few lines of code. Right? It's some just repackaging of what you've already done, and the rest is fairly minor modifications to what you've already done. So this is all about, getting everything lined up just so. Getting all the parts and pieces to play together. Say again?
Could we rename all those Q add and Q whatnot, just the letter Q?
No.
I cannot imagine how much time I'm going to spend spelling Q wrong.
Oh, but you'll be really good at spelling Q by the end. Or use the letter Q and then just do a global substitute at the end. But yeah, this is a free bonus. You get to learn how to spell Q. And someday that'll come in really handy. And you'll look back at 222 and say, well, I don't code anymore, but, I just got this great gig at this wine auction house because I spelled Q properly. So, all right. Yeah, it's a prophecy. It's not in the course outcomes, but it could happen. All right. So your main program should report, errors if you try to pop from an empty stack or you try to remove from an empty queue, and it should report syntax errors if you type in something that's not a valid integer, if you type 2.5, or if you type, a command that's not recognized. It should report those syntax errors. But your functions for popping and removing don't need to worry about the queue being empty. If that happens, just don't do anything. Don't throw up, right? Don't segfault or something. But I will not call those functions when the queue or stack is empty. Okay, I'm going to be a responsible user and always check is empty before I call pop or remove, and your main program should do the same thing. You also don't need to check for running out of memory when you add or push or when you do your inits. Alright, so same program structure. Main.c is your main program, and any other functions you write for your main program. Functions.c, which is those required 11 functions and any other functions used by those. Right, so if you're going to repurpose, some code from PA1, that goes in functions.c also. And the main.h, which is the my struct definition, struct my node definition, and the function prototypes, and then a makefile, which includes a clean target to remove main.o, functions.o, and main. So your choice if you want to reuse code. Sorry, go ahead.
You said only 11 functions, so we can have helper functions and stuff, right?
Absolutely, yeah. My test code will call these 11 functions and exercise them, but you're welcome to have as many functions as you want that are used by these or for debugging or whatever else.
Will you then use our main.h because those functions are going to be declared in that?
Yeah, I'll use your main.h and well, if you, yeah, that's fine.
Okay, because I did that in PA1 and obviously you must have.
Yeah. Because I don't think I'm going to have any function names of my own that are going to conflict with what you do. So yeah, that should work fine. All right, let's see. So your choice, how much code, if any, you want to reuse from PA1. Sample program on the server, temp PA2 sample. We'll play with that in a minute to see what all of this stuff means in practice. Deliverables, so make a tar file, pa2.tar, containing those 4 files. Make file, functions.c, main.c, and main.h. And there's a tar command for creating it, upload it to Canvas by the deadline, and if you had issues with tar, or even if not, right, I recommend copying the tar file that you're going to upload back to a Linux machine, untar, make, test, just to double check. Alright, so submission shouldn't, go ahead.
How do you untar again?
So untar with,
RX VF or something like that. Or RX. Yeah, XVF.
right, so extract, verify, file name, pa2.tar, and this will dump into your current directory all the files it finds in here. So don't do this in the same directory where your actual live code is. Make a new directory, copy the tar file into that new directory, and then untar from there. Because it'll just step on files, and if this is corrupt, you might lose your files.
Always use a git repo.
Always use a git repo. Alright, so submission should include complete implementation of a linked list-based stack and queue. Main program for testing these as described above. Plenty of commenting. Okay, again, for each function, list its name, purpose of each input, purpose and meaning of any return value, and so on, and a block of comments right before the code of the function. Code should be commented throughout. Main program should also be commented. Comment block should be in the beginning of your main program, containing all that usual stuff, and you need to have a make file. For creating an executable image, which must be named main, and this should build the program with a single command make and have a clean option. And then grading is very similar to PA1, so a set of sort of mandatory deductions. If I can't get to your stuff, it's 100% off. If I can't compile it, it's 50% off, and I'll try to fix it so I can grade the rest of it. If you don't use the right function names, if you don't use the right name for your structure, if you don't use the right names for any of that stuff, 50% off. If it's not split into the right 4 pieces, 35% off. And if you're doing something totally different, if you decide to implement this using arrays instead of linked lists or something, that's 100% off. So you got to do this with linked lists. And then assuming it's gradable, right, makefiles 5%, push and pop are 14% total, 7 points each. Queue add and remove are 7 points each. Correctly moving between stack and queue mode, 10 points. Correctly printing the stack and queue, 10 points each, 20 points total. Main program works perfectly, 10 points, right, including all of the syntax checking. No memory leaks or valgrind warnings, that's another 10 points. No compiler errors, that's another 5, and then 3 points for each of those 4 style issues. Comments before each function, comment block in main, comments throughout the code, and consistent indenting. So pretty similar to PA1. All right, so let's take a look at a sample of PA2. So temp PA2 sample, all right, there's the program, demonstrates the use of a stack and a queue. I don't care if you print a help message in the beginning or not. It's up to you. So I'm sitting in stack queue right now, in stack mode right now, but there's nothing on stack, there's nothing on the queue. If I print an S, it'll show me stack is empty. If I do a queue, it'll say, you know, switch into queue mode, and there's the head, there's the tail. I don't care if you say stack is empty or just say TOS arrow nothing. I'm fine with either way. So let's go back into stack mode. Let's push some things onto the stack. Let's push a 2 and a 3 and a 4. Here's what my stack looks like. Right? I pushed a 2, I pushed a 3, I pushed a 4. 4 is at the top of the stack. That's the thing that's going to be popped first. Let's go into queue mode and let's add an 11 and a 12 and a 13 and a 14 and a 15. So if I look at my queue, this is what it looks like. 11 is the first thing I added. That's at the head of the queue on the left. 15 is the last thing I added. That's the tail. If I want to remove an element, I'm just going to hit enter and it shows me 11. And now if I look at the queue, it shows me my queue. It's got a 12 sitting at the head and a 15 at the tail. And I can remove 2 more elements. There's my 12 and my 13. Here's what my queue looks like. And now I can add 20, 21, and 22, and those get added at the tail. Meanwhile, I can switch back to my stack, which had a 4, 3, 2, and I can say, let's pop the last thing on the stack. Just hit enter. There's the 4, and my stack has a 3 and a 2. And I can push some more things, 11, 12, 13. If I look at my stack, there's the 11, 12, 13. 13 is the last thing I push. That's the head of the stack. And if I hit enter, it'll remove. There's the 12, there's the 11, there's the 3. I've got one thing left on the stack, which is a 2. Hit an enter, it removes the 2 from the stack. If I look at the stack, it tells me stack is empty. If I try to pop from the empty stack, it'll say error, stack is empty. And I can push some more things on the stack. There's my stack. Meanwhile, I can go back to my queue, which still has all the stuff on it that I had before. And I can remove from the queue, so there's the 14, 15, 20, 21, 22. And my queue is empty. And if I try to remove one more thing from an empty queue, it says error, queue is empty. So now my stack is empty again and my queue is empty. Alright, that's pretty much all your program does. Right? You can be in stack mode or queue mode and you insert by, typing numbers. And with queues, there's no question of duplicates, there's no question of sorting things, right? When you add something to the queue, it puts it at the tail, and there it is. And if I want to add a bunch of zeros, I've got a bunch of zeros in the queue. Yeah.
You're talking about the queue where you do that interesting way of wrapping around and end of queue. That's for arrays only, right?
That's for arrays only, correct.
Okay, so for this, it's just order n always.
For this, it's order n unless you do the tail pointer trick, and I think I mention in here that it's up to you. So on the queue add, it says it's up to you whether to or not to implement a tail pointer or simply traverse to the end of the queue. So you can do it either way. And we're not worried about performance here because our queues aren't going to get that big. Although this queue is getting pretty huge now, right? But either way, if you want to play with tail pointer, it's kind of fun. But if you want to just loop through until you get to the last node because it's pointing to null, that works just fine. Right, so 4.5 is not a legal integer. Haha is not a legal integer. So everybody got the idea how the program should behave?
Yes.
Any questions so far on how you're going to make this happen? On how to implement this?
How do you switch between stack queue mode? Did we cover that already?
You mean from the user perspective or from the coding perspective?
Either or both.
So from the user perspective, it's just S or Q. Right now I'm in Q mode. If I want to be in stack mode, I'll just type in S. And now I'm in stack mode, and enter removes, and typing a number pushes.
I guess I meant from the coding perspective then.
Yeah. So how do we make this happen? So this is stateful programming. So we need a flag, right? So we might make, an integer called mode. And let's say 1 equals stack and 2 equals Q. And I'm going to initialize mode to 1 because it says the program should start in stack mode. And so when you read input from the user, if the input is an integer, then you're either going to call push or you're going to call add. Which one do you do? It depends what mode you're in. So you might say, if mode equals 1, which is stack mode, then push whatever number the person typed in. If mode equals 2, then add. So our, let's be precise. Our push function takes a pointer to the sentinel node and then a number. Our add function takes a pointer to the sentinel node and then a number. So if mode is equal to 1, then we might want to push, my stack, comma n. If mode is 2, then we'll want to add my q, comma n. We're somewhere in the beginning, I said my stack equals init, and my q equals init. So in my main loop, I read a line from the user command, and if they typed in an integer, I'm either going to push it to my stack or add it to my queue. If it's a p, then, if mode equals 1, then I'm going to call, stack print. Stack print my stack. If mode equals 2, or maybe, I'll just say else qprint my queue, and so on. So it's like PA1, except that once you've decided this person's trying to insert something, this person wants to print, this person wants to, you know, remove something, right? You look at your mode variable to say, hey, should I be operating on the stack or the queue? And you have a pair of statements depending on what the value of mode is. And then if the command is S, what do? We don't have a print command, that's bogus, but you know, work with me on it. If the person types an S, right, that means they want to go into stack mode. So change mode to 1 and then call stack print. So this is bogus. But if they type an S, set the mode to 1, call stack print. If they type a Q, set the mode to 2 and call Q print. If they hit an enter, check the mode. If mode is 1, then call stack pop. If mode is 2, call Q remove. Does that make sense? So this is stateful, and again in that additional textbook on Canvas, there's a chapter on stateful programming, and these chapters are, you know, like 8 pages long or something, but it goes through this idea in more examples. And this is a really powerful idea. This is something you can use a lot. This idea that, you know, the person hit enter, what should I do? Should I pop from the stack? Should I remove from the queue? Should I say syntax error, right? It depends on what state the program's in. And so this is a useful concept in general. Yay, it's Amazon at the door. All right, other questions? And this by the way, is a classic example where you could use defines in C, because I have this magic value, right? Mode is 1 for stack and 2 for queue. And I have to remember down here, you know, to check if mode is 1, do my push. If mode is 2, do my add. But this is a case where you could use some defines. So you could define stack to be a 1 and define queue to be a 2. And now I could, you know, write those same statements but say something like, you know, if mode equals stack, do some stuff. And it minimizes the chance of, you know, coming back late at night and thinking that 1 means a queue and 2 means a stack and swapping these. And if you do that, you know, you're not going to get a compile error, and your code's going to kind of look like it works. But if you look at your test cases carefully enough, you'll figure out that, like, when you're in stack mode, something's happening to the queue, you know, and something's getting corrupted, and it's going to be really confusing, and it's just a typo, right? So if you can avoid these magic numbers, because 1 doesn't mean stack, 2 doesn't mean queue, that's just a convention that we're adopting. But if I use these defines, right, and then I use the word stack or the word queue, right, these magic values are, the particular value of those are irrelevant. And so that's, you know, where you can use these defines. So let's see, anything else in here? Cleanup is just, you know, clean up, and at the end you just want to clean up your, so in the beginning you definitely want to make yourself a pair of linked lists, right? So these will both be, you know, struct mynode stars, and make a list for your stack and a list for your queue. You can call them whatever you want, but don't call them A and B. Call them something meaningful to you, right? Unless A and B are meaningful to you. Call them, you know, my stack, my queue, or something like that. So those get initialized by calling a init. And that's just PA1's init. And then and then push and pop, right? So insert right after the sentinel, remove the node right after the sentinel. You don't have to catch pops from an empty stack, but don't segfault, right? So if the sentinel is pointing to null, stack push, you can just return. Just don't do anything. Or stack pop, just don't do anything. Stack is empty, just check to see if the sentinel is null. If it's pointing to null, and if sentinel next node is null, the stack's empty. And then stack print, print out the header, and then just traverse the list.
Any question?
Yeah.
So if the user runs the program, what mode do you want to default on? I mean.
Oh, program starts in stack mode.
Okay, thanks.
So program should begin in stack mode. I should probably bold that or something. And if you want to print a message in the beginning saying, we're in stack mode, that's fine. All right, and then Q init's just the init. Q add, either travel down the list, right? Make yourself a while loop, like in your print statement, but instead of printing, just keep moving from node to node until you get to a node that's pointing to null, right? Don't go past the end of the list, but go to the end of the list. So you can do something like this: temp equals sentinel well, temp next is not null. Temp equals temp next. This is a really good exercise to get ready for the midterm, by the way. Just this 3 lines of code right here. What I'm trying to do here is, starting from a sentinel, I want to get temp to point to this last node, right? If you can reproduce this, that's a good check that you've got a pretty solid understanding of how these pointers are working and how to come up with an algorithm to manipulate these, right? So when we print, we normally start with, sentinel next node, and we go until the thing we're looking at is null. Well, if we do that here, when we come out of our while loop, temp is going to be null. That doesn't do us any good. And we could set up a previous and a current, and then previous would point to it. But we can also, make a simpler loop, which simply begins with temp right here. And as long as it's pointing to something that's not null, move to that thing it's pointing to. Move to that thing it's pointing to, move to that thing it's pointing to, move to that thing it's pointing to. But when we get temp out here on the last node, temp next will be null. We will exit our while loop. And so when we come out of this curly bracket, temp is the last node. And if our list was empty, if it was just a sentinel, we would initialize temp to be the sentinel. Temp next is null. We never do the while loop. Again, temp is pointing at, effectively the last node. Or rather, temp is the thing that we should change to point to our new node. So that's one way to do it. But like I say, this is a good sort of self-check exercise. So so once you have temp or something, pointing to the end of the list, make your new node, store the data value, have your new node point to null, and then have that last node point to your new node. All right. And then remove is just like pop, right? You can probably just rebundle the pop code because you're just going to remove the thing the sentinel points to. And you don't have to worry about doing anything in particular if you try to remove from an empty queue. If you have an empty queue, the sentinel will point to null, so don't segfault, right? Don't try to free the thing that sentinel is pointing to. Just notice that the queue is empty and just return. And then is empty is the same as stack is empty, just see if the sentinel's pointing to null. And then print is the same print routine, but print this before and print this after. Cleanup is PA1. Of course I'm going to read something if you say don't read that.
Man, don't read aloud.
These are lessons from my 4th grader. If you want to get her attention, just like whisper something, you know. And it's like, what? What did you say? All right.
Your axe,
Sorry.
or mention your axe.
Yeah. Let's see. I think that's pretty much everything. So this is due a week from Friday. And you should have enough information to make a good stab on this, like, right now. I mean, there's nothing else we're going to talk about that's going to really sort of, you know, be critical for this. We're going to switch gears and start talking about hashes next. So, so you should have everything you need to get going on this. And again, you know, use the test program on the server to double check the behavior. Yeah, go ahead.
How would you check if the user entered nothing to set a curiosity?
Yeah, so let's talk a little about the parsing, because the parsing is a little weird. So we're going to use fgets as usual. So let's do something like, you know, fgets into some character buffer. All right, and you're just going to do that, you know, in the beginning of your loop. So print a prompt, do an fgets. And then we have to decide, right, did they type a magic command, did they type an integer, or did they hit enter? All right, so how do we know if they typed enter? An easy way to do that is see if the first character is a new line. If the buffer that they type in begins with a new line, they didn't type anything on the line, they just hit enter. And remember, fgets always appends a new line to the end of the input as long as it fits in the buffer. And so if they say hello, buffer will be HELLO new line. If they type a 5 and hit enter, it will be a 5 followed by a new line. If they just hit enter, it will just be a new line. So you could check if buffer 0 equals single quote \n, that's the character for a new line, ASCII code 10. Or you could do string compare and see if buffer equals double quote \n. So those are two options. You could do an scanf on buffer, %d, %s, address number, extra. So scan the if they didn't just hit enter, you could run buffer through scanf and look for a pattern consisting of an integer followed by anything else. And if scanf returns 1, it means that buffer matched the pattern of an integer with nothing else after it. That's a good integer input. So if this scanf returns 1, person typed in an integer, check your mode and either call push or call add. And yeah, you can check for a \n in an enter in a switch statement. That would work fine. And then you can check to see if they typed an S or a Q or an X. And I think those are your only legal commands. S for stack mode, Q for Q mode, integer to insert, enter to pop, and then X for anything else. So those are your only 5 cases. Otherwise, there's a usage error. So one thing you can do is, do this first. Check to see if there's an integer. And if not, all of these other conditions really just depend on what the first character of buffer is. So that's a case where you could say switch on buffer bracket 0. And do your switch statement. Different cases have a default catch-all. All right, cool. Other questions?
I'm not sure if you covered this, but one of the requirements in the PA2 was that we would have to make a Git repository.
No, so I said a while ago, ignore the instructions about Git.
Oh, okay.
And I've modified the PDF and I'll post it right after class. Yeah, that was a leftover typo from another README that I was repurposing. But, use Git for your own if you like it. But it's not part of the assignment. All right, anything else? All right, we're going to shift gears. We're going to go back to talking about associative arrays, which are also called hashes or hash tables. And the idea here is one of the ideas here is to speed up our search time and our insert and our delete times better than we can do with a linked list. And theoretically better than we can do with binary trees, which we're going to come to after we do hashes. And theoretically, a hash will approach an order of performance of 1. Theoretically, we use a hash to store a bunch of information, and we can retrieve that information in a fixed amount of time, no matter how much stuff is in the hash. And that's not practically achievable, but we can get close. And the thing that makes that work is an associative array. So let's review associative arrays from 224. So if we have a plain old integer array called x, bracket 10, x contains 10 integers. And we can access those integers with x bracket followed by an index, x bracket 0, x bracket 1, x bracket 9, and so on. Or, if I have an integer I can say x bracket I, as long as, I is between 0 and 9. So that's a plain array. An associative array we can also do things like x bracket hello, or x bracket negative 237, or x bracket 12.5, or x bracket, something that, might be a pointer to a memory address. Or we could also, do x bracket 0, x bracket 1. But we can use pretty much anything for the index of this array. And anything is valid. And so we saw how to implement these in Bash, so that you could take in something like, you know, a word or a phrase or a sentence and use that as an index into an array called tally, and you could store, you know, how many times you saw that word or that phrase as an element in this array. So let's imagine that we want to store license plate information. So we have, you know, a plate number, and we have a name. And so here's ABC123, and this is my license plate. And here's, you know, PQX567, and that's, you know, that's Izad's license plate, and so on. And so you're going to have, you know, some sort of thing in memory that stores this information. And your goal is, you know, if I give you a license plate, I want you to tell me what the name is associated with that. And so we could do this with just a pair of arrays, parallel arrays. Make an array of plates, make a corresponding array of names. And now if you want to know, you know, who does this license plate correspond to, you just start checking this array of license plates. And when you get down to element, you know, 10,005, you find the license plate. Well, element 10,005 in the name array tells you the name associated with that. So we can do this with plain old sequential arrays, but it's really inefficient. It's order n. If you have a million license plate, it might take you a million operations to find the plate you're looking for, because it might be the last one in the array. And then, you know, you say, okay, well, that corresponds to, and you just pick the last name in the array. But that's expensive. And so if we were to sort these, we could do an order log n. We can play high-low, right? Look at the middle point and read strict R search to either the top half or the bottom half. So relatively fast search operation there. But if we want to add something to the array, that becomes order n again, because if we want to add something in the beginning, we got to push all these names down, right? If our new license plate comes alphabetically before any of the others, we'd have to move a million elements of the array to make room and move the corresponding elements of the name array. So when we get to binary trees, we'll see a way to do this with order log n for both insert and search, and also for delete. But an associative array lets us do this in basically order 1. And so I would make an associative array called plate, and I would store the following values in this array: plate bracket quote ABC123 equals Nick. Plate bracket quote PQX567 is going to have the value Izad, and so on. And when I have a new license plate I want to add to my data, I just simply say plate bracket that new plate equals, you know, whatever name that is. And then when I get a license plate and I want to know who does that plate correspond to, I can say plate bracket such and such, right? And I can just say my owner is, you know, whatever value is stored in that element of the array. And if that plate doesn't exist, this will return something like null, you know, or an empty string or something like that. And I'll say, hey, that plate's not in the database. So if you have an associative array, an array that you can index with, say, character strings, right, we can tackle this problem very simply. Simply use the license plate as an index, and at that element in our array store the corresponding name. And if the implementation of this associative array is efficient, everything is order 1. When we look for a plate with this, it comes back right away and either tells us the corresponding owner or says it's not in there. Right? Just like when you have a plain old array that you index with consecutive integers starting from 0, accessing the ith element takes a fixed amount of time. It doesn't matter how much stuff is in the array. There's no search for, the 9th element of the array. If we want element 9, there's a formula we use to tell us where in memory that element is stored. For an integer array, x bracket I is stored at whatever the address of the first element is, plus 4 times I. This is assuming that integers take 4 bytes to store, and so the address of x bracket 0 is where the first element is stored. The next element will be 4 bytes after that. So if my array begins at location 100, so if x begins at memory address 100, x bracket I is at location 100 plus 4 times I. If I want the 15th element of my array, x bracket 15, it's going to be at location 160. Why? 15 times 4 is 60, plus 100, 160. So with a regular array, when you know the index, you can calculate where that element is stored in memory. We do exactly the same thing with an associative array. But the formula is more complex than this, because the index is not a simple integer. So here's the whole idea. With an associative array, let's call it x, there is a formula for locating element x bracket I, where I may not be an integer. It could be a string, it could be a license plate, it could be a JPEG of somebody's front yard. It could be a sound sample from a song that you're trying to find track information on, right? So there's a formula given the index for figuring out where that element is stored. And so if I have, an associative array storing license plates and I want to find the plate corresponding to, some string, I run that string, that index, through the formula, and it tells me, hey, either it tells me this thing is not stored in the array, or it says, oh yeah, it's stored over at that location right there. And then I just go to that location and I grab the data. Alright, is this making sense, like what the goal is here? And sort of the high level behavior of this? The magic is, what is this formula? That's where the details come in. But effectively it's the same thing as an integer array. Yeah, go ahead.
I was thinking like some kind of algorithm to kind of speed this up. Like, instead of going through this one by one, if it goes alphabetical order, it would be a lot easier to find it if you just you can search for them. Well, yeah, it was an idea, but I think it's still order n, because you still have to go through the list. So I was thinking like ordered by a letter, or the order by alphabetical order, and then so it's easier to track, or easier to find the person associated with the license plate.
Mm-hmm. Yeah, so if you alphabetize, you can get into faster searches by doing like divide and conquer, split your list in half and search either the first half or the second half, that kind of thing. But if it's a conventional array, you still have troubles with inserting and to some degree deleting, because stuff is packed in next to each other. With an associative array, the stuff could be all over the place in memory. It won't be. It'll actually be close to each other. but we have this way of turning an index into a location that hopefully, you know, even as we add stuff, this association doesn't change. All right, so this formula, this is called a hash function. And a hash function is something that basically takes, you know, something like a license plate. It might take a string ABC123 and give us back, you know, some numeric piece of information that tells us where the name corresponding to this is stored. And rather than just storing these things randomly in memory, we're actually going to store them in an array. So our hash table is really going to be a plain old array indexed with, you know, consecutive integers starting from 0. And our hash function is going to take the index that we want to use and map it to one of these values. And so if I put in the license plate, you know, ABC123, and I put that through my hash function, it's going to give me, I don't know, maybe it'll give me a 3. And at location 3, that's where I'll store the value associated with it. And if I put in the string PQX567 to my hash function, it might return, you know, the integer 5. And so at location 5, I would store the name associated with that license plate. And so assuming my hash function, you know, does not depend on how many things are stored in the hash, which it doesn't. It's just something that in this case takes a string, returns an integer between 0 and whatever this last index is, right? I get a license plate, PQX567, I want to know what the name is. I run it through my hash function, takes a fixed amount of time, it gives me a 5. I go to location 5, takes a fixed amount of time, there's the data associated with it. And so theoretically, this is all order 1.
How does this associative array work in a way that, you know, makes it order 1? Because what's the computer doing that allows it to just instantly access these elements?
It's magic. It's using this magic hash function, which takes the index and turns it into a numeric index in this big array. So for example, my hash function could say, add up the ASCII codes of each character in this string. And let's say, you know, we have 100 things in our array. Add up the ASCII code of each character in this string, and then calculate the remainder when you divide by 100, right? Take the last 2 digits of the sum. That gives me something from 0 to 99. Whatever number it gives me, that's the location where I'll store the data associated with that license plate. And so someone asked in chat just now, won't it run into conflicts? Yes, it will. And that's where reality and theory sort of separate. And so we can get collisions or clashes. Because it's possible that 2 totally different license plates, my hash function might map into the same location. In fact, if my hash function always returns something from 0 to 99, if I have more than 100 license plates, I'm guaranteed I'm going to have a conflict. There's going to be at least 2 license plates that hash the same thing. If you've done 215, it's the pigeonhole principle. Right, so we will have collisions, but theoretically, this is order 1. Right, if we don't have collisions, if we have enough space in our hash table, and we do a carefully chosen hash function, different license plates will map to different indices, and everything will get stored in its own location. So a lot of the details of this has to do with what do we do when there are collisions. So I think we can call this a hash function that takes a string and returns an integer in this case. And it is a function in the vertical line sense, right? It's just not one-to-one. There's multiple things here that'll map to the same value. So it's not surjective. Again, if you've done 215, it's not surjective. Well, it's not injective, and it may not be surjective. But if this was, you know, injective, we'd have no collisions. Different keys would always map to different values. So a lot of the details we're going to start going through next week have to do with, you know, the detailed behavior of this hash function on real world data, and then looking at different kinds of hash functions that can map, you know, from these strings to integers, for example. And then looking at what we do with collisions. And there's different ways we can deal with collisions. One way is to use something called probing, which we'll talk about in detail. But another way is going to be to use, guess what, a linked list, right? So we'll talk about both of those. All right, so that's an intro to hashing and hash tables and hash functions, and we'll dig a lot deeper into that starting on Monday. So hop on to PA2 if you have the time. Come by office hours if you got questions or if you want to go over PA1 more. I will see you in 2:15 if you're in there. Otherwise, have a fantastic weekend, and I will see you on Monday. And still planning to be remote until further notice.